Get to the section where we're going to explain the power radiated from an object. This is known as the equation for radiation. So we'll go over the theory. This power is equal to the surface area of the object times sigma and times E times T to its temperature to the power 4. So notice that since the power radiated from an object depends on temperature, the temperature must be in Kelvin. It cannot be Celsius because it doesn't depend on the change in temperature. It depends on the temperature. So what does the surface area means that the bigger the surface area of the object, the more power it will radiate, right? So it will lose heat faster. The sigma is a constant that's uniform throughout the universe, 5.6696 times 10 to the minus 8 watts per meter squared Kelvin to the fourth, right? So the units of power has to be in watts. The surface area A is going to equal meter squared, and then T is going to be Kelvin to the fourth. So when you do the sides of the equation, they should both be in units of watts, right? And then E is equal to the emissivity of the object, right? And it's basically a unitless number, and it will tell you how much that object emits radiation at what ratio, right? Emissivity of a black object, emissivity black is equal to 1, right? So if it's emitter of heat, its emissivity will be 1. Then there's another constant called absorptivity, A. Absorptivity is written like this, absorptivity. And the way that absorptivity is defined is that it's the fraction of the incoming energy that the object absorbs, right? The ratio of the incoming energy. So how much energy is coming in from its surrounding, how much of that energy the object absorbs. And then emissivity is how much of its energy the object emits. Well, it ends up that the absorptivity is also equal to the emissivity. It's equal to E. So if the object is a good emitter of radiation, it's also a good absorber of radiation, right? So the absorptivity of black and the emissivity of black is both 1. A of black. Right? So if you are wearing a black shirt, right, you're going to be emitting a lot to your surroundings, but you're also going to be absorbing a lot from your surroundings. So the power emitted, we can write it as A sigma E T to the fourth, the power absorbed, power fourth. So this is the emissivity and this is the absorptivity, right? Well, since the absorptivity and the emissivity are the same, this just becomes A sigma E T to the fourth. The only difference between them is this is your temperature because you are emitting the radiation. So this is the temperature of the object. And then you're absorbing heat from the surrounding. So this is the temperature of the surrounding. Temperature surrounding. So the total power that you're going to radiate and the total power that you are absorbing, you take the difference of the two, right? So this is going to equal the power emitted minus the power absorbed is going to equal A sigma E T to the fourth. This is the object, right? And then minus T of the surrounding to the fourth. So if the surrounding is hotter than you, you're going to absorb a lot if you're wearing black. And if you are hotter than the surrounding, you're going to emit a lot if you're black. So in the winter, if you're wearing a black shirt, your body is going to be hotter than the surrounding, right? So you're going to be emitting a lot. So it's not good to wear black because you're going to lose a lot of heat. In the summer, the surrounding is hotter than you, and you're going to be absorbing a lot, and you're going to sweat. We can give some numbers so you can see example of this. In summer, let's say the temperature outside is very hot. Let's say it is 50 Celsius, right? So then convert that to Kelvin, add to 273 to it, you get 323, right? The temperature of the human body is 37. So 37 plus 273 is 310 Kelvin. So in the summer, your temperature is 310 Kelvin, and the surrounding is 323 Kelvin. So you're going to be absorbing a lot, right? So that means the power absorption is going to be larger than the power emission. So we can say P total is equal to P absorbed minus PE. So it's going to be A sigma E T surrounding to the fourth minus T object to the fourth. right? The A will be the surface area, right? Human is 0.8 meters squared. Then we multiply that by 5.6696 times 10 to the minus 8, right? Watts per meter squared, Kelvin to the fourth. Now, if you're wearing completely black, right, then the emissivity is going to be 1, and absorptivity is also 1, so we just need to use the 1 here. And then the surrounding is going to be 323 to the fourth minus 310 to the fourth, right? So you're going to be absorbing a lot. So we can say roughly, right? So that's how much heat you're going to absorb. That's 74.8 joules per second, right? So in 1 minute, you're going to absorb 74.8 joules times 60, right? Since this is 74.8 joules per second, if you multiply it by 60, you get how many joules you're going to absorb in a minute, right? So your body temperature is going to rise, so you're going to start sweating that out, right? We can do a calculation if we knew the specific heat of a human. We can do a calculation into how much your temperature will rise, how much you will sweat, and so on and so forth, right? So you can see it's not good to wear black. If you weren't wearing black, let's say you just had your skin out, the emissivity of natural skin is roughly around 0.9. Emissivity of skin, 0.9, right? So then you will emit a little bit less than this. Well, in the winter, what's going to happen? The opposite, right? So in the winter, let's say on a really cold day, let's say it's 0 Celsius outside, right? So then what's going to happen? 0 Celsius is equal to 273 Kelvin, right? So then your temperature is going to be still the same, 310 Kelvin, right? So then what's going to happen? So then it's going to be power total is going to equal power emitted minus power absorbed, right? In the winter, you're going to emit more than you absorb, so then it's going to be so that's even more than the summer, right? 166.9 watts, it's about twice the summer, so you're actually radiating a lot of heat and you're going to feel cold, right? So it's better, therefore, either to just have skin or to have a different color shirt that has a different emissivity, right? You could also relate this to the Earth. The emissivity of the Earth, which is also equal to the absorptivity of the Earth, is about 0.67. Okay, there's also another quantity called albedo. Albedo is equal to the ratio of the energy received from the surrounding that the object reflects. So the ratio of energy reflected by the object. And the albedo of the Earth is equal to roughly 0.33. So we can see the albedo plus the absorptivity is equal to 1. Albedo plus the absorptivity is equal to 1. So the absorptivity is 67% for the Earth. So the Earth absorbs 67% of the energy that it receives from the sun and reflects 33%, right? So over the course of the last few years, the albedo of the Earth has been decreasing by about 1% per year. If this number decreases, that means this number increases, right? So eventually, let's say over the thousands of years, let's say the albedo of the Earth were to drop to 0.25, right? And let's say the absorptivity increases to 0.75. Right? So together they have to add up to 1, right? So what would that mean? That means the Earth would absorb 75% of the energy that it receives from the sun, and it would reflect 25%, right? And then on top of that, the Earth would re-radiate that energy because the emissivity and the absorptivity are the same, but the Earth re-radiates that energy at a lower temperature, since its temperature is lower than the temperature of the sun, right? So what would that mean? The temperature of the Earth would rise through the course of the years, right? The temperature rises as the albedo drops, right? Due to universal global warming, and this is something that we need to be very careful of, okay? So through this theory section, you can see what effect that the emissivity has, how the emissivity is equal to the absorptivity, and then this other quantity called albedo, how they are all related. How this is related to the temperature that something reaches as a result of the interchange of energy between it and the surroundings, okay? Thank you very much.